using a new and very capable combination of science instruments. And we've heard a little bit about that already. There's the MET station on board. There's the special unique opportunity given to us by coordinated observations with the Mars Reconnaissance Orbiter. And I'll also talk a little bit about how we're using all the instruments on the Phoenix lander to give supporting measurements that help us interpret what's happening in the atmosphere. In today's update, I'm going to talk about a summary of our weather observations from sols 1 to 63. And where we are now, we landed in the late springtime on Mars, and we have been following the late spring through into summer. We're now at Sol 65. We're in high summer on Mars, and we're heading towards Sol 74, which is the peak of when we expect to see maximum water vapor around our site. And this has been from the sublimation of the water ice in the North Polar Cap and its transport southwards towards us. So this is, for atmospheric science, the longer this mission can last, the better. And we can really start to follow seasonal changes and understand the very complex picture we have. What I would like to report on first is something that we've been very, very pleased about. What's new to report is that spacecraft power has actually been very, very good, and it's allowed us to extend our atmospheric measurement set into the night time. Now, because we're in the high Martian Arctic and we're in summer, that the sun doesn't actually go down below the horizon, but it dips very low, and it does give us darkened skies. And we took a very special measurement on Sol 61. Again, something we really didn't expect ever to be able to do. What we've been able to do is look upwards with the surface stereo imager and actually image the MET LiDAR beam. So what I want to show you now is an image of the MET LiDAR beam that's been taken in a green filter with the SSI camera. And if we could bring that up, please. So this is absolutely an amazing image. What we're looking at here is essentially a laser light show on Mars taken with an instrument with the power of a 30-watt light bulb. And we are seeing that from 200 million miles away. You know, this is absolutely astounding. Now, you know, as well as being a very, very cool image, this is also a kind of a regular image in our atmospheric science data set in terms of what we're looking at. We're looking upwards, and we're looking at, we've got the LiDAR beam in front. It's the first time we've ever done that. If we could go back to the LiDAR beam, please. But behind it, we can see essentially a movement of the dust in the sky moving past the beam. This is at some kilometers further back. We're able to see the first 1.5 kilometers of the LiDAR beam as we're looking up in this steep angle. But we're able to see the background sky, and from the motions that we can see there, we can estimate wind direction at height, which is an important measurement for us. What we're also able to do with the combined LiDAR beam and the SSI image here is where the pixels overlap with the LiDAR beam, we can actually extract useful information from the SSI image that will help us with the composition of the particles, things like that. So this is an exciting addition to our atmospheric data set. And what I would like to do now is just go on to our summary report of what we're seeing overall at our landing site. And again, just to put us back in context, we have been looking late spring through to midsummer now. And to remind you of all the different types of instruments we're using, we're making daily measurements with our MET station, and that includes pressure and temperature measurements, winds with the telltale sensor, and our LiDAR to give us vertical profiles and information about the dust and the cloud structure. We're also combining that with our Mars Reconnaissance Orbiter special coordinated observations, which we're trying to do every 10 days or so, to actually look down in the same column of the atmosphere. This is going to be a very, very powerful way of extending what we learn at this single site to what's actually happening over the whole Arctic region. The other instruments that we're using SSI in combination with the MRO passes there to give us water column information and also tell us about the dustiness. But we're even using the robotic arm. So on the days when it's having a rest from digging, we're actually using it with a TCP sensor to give us near-surface profiles of humidity and winds. So it's really a very comprehensive and quite a complex data set. We're even looking at things like dustfall with the optical microscope with MECA. So this will be put together over a long period of time. What I'd like to highlight now is the very regular measurements we've been getting over this period. We did expect the summer period on Mars and the high Arctic to be fairly calm, and we haven't seen any major weather systems pass over our lander at this time. Temperatures, the maximum and minimum, we're seeing big changes throughout each day, but we're not seeing significant changes day to day. And that goes for all of our measurements, apart from pressure. And here I want to highlight two types of observations we're seeing. With pressure, we're seeing a slow daily decrease in pressure. And this is to be expected. What this is related to is the condensation of a significant part of the carbon dioxide atmosphere on the southern pole, which is actually in winter just now. And it's quite remarkable, though, though this is an expected result, it's remarkable that we're actually able to measure this change at the high Arctic in the north. And that's been quite interesting and exciting to see. The other thing I want to talk about is our telltale measurements. And because we've had such steady conditions over this mission, what we've been able to do is we're able to combine the measurements we're making on several successive sols to give us a detailed picture of what's happening in a typical summer Martian sol. And if you bring up the animation now, what we have here is we've combined our measurements. These are 2-minute measurements spaced apart, and we're looking from 10 a.m. on a typical Martian sol through to 6 p.m. The telltale is about 4 inches high. It's about 2 meters off the ground. And what we're looking at is the little mirror in the bottom of the image there. The X you see across it, the bottom right-hand corner is actually indicating north. So what we see over this day is we see the winds are starting being kind of southerly. We see the deflection of the little bob in the mirror telling us which direction the winds come from and how much it's deflected. We've actually calibrated to give ourselves a fairly accurate measurement of wind speed. So we're seeing the winds change direction over that day from starting in southerly, moving over towards westerly, and we actually, if we fill in the day through the night, we actually see that go over to easterly, and that's a weather pattern that is what we would kind of expect to see. The maximum wind speeds we've seen are about 7 meters per second or 15 miles per hour. And what we really want from the wind information, it's kind of critical to helping us understand what the transport is in this whole area. So where the wind is coming from tells us a lot about how to begin to interpret the data we're getting at this landing site. And what I'd like to do now is move to an image that is going to show us how local topography might be influencing what we're seeing. So how the landscape might be actually influencing the wind directions we're seeing, and how much our local site is responsible for the patterns we're seeing in the data, and how representative we are of the whole region. So we landed in Green Valley, and we've now zoomed into Green Valley. This is a very shallow valley in a very flat region. We wanted to go to a very flat region. This is very good for a number of reasons. It's very representative of a large area, so we can extend the measurements we're getting at our landing site and feel that it's representative. It's also for making it for landing reasons, we wanted to go somewhere flat too. So we weren't looking for steep topography. And the valley sides here are about 250 meters high. The valley's indicated in blue. And what we actually find with our wind speeds is, especially those easterly nighttime winds that we've picked up, we're actually seeing that the local topography, despite this great flatness, is actually having some influence on the data that we're getting. We're seeing slope flows down the valley sides are actually influencing our landing site. Even though, as you'll see, it's very flat, these very shallow slopes of 1 to 2 degrees are enough to actually give us these nice cool breezes. We see the cold temperatures at night in the temperature data as well.